All right, this is lecture 3.1 covering functions and function notation. We're going to go ahead and jump in because this is a pretty thick section to get through. Okay, welcome Ashley. Glad to have you tonight. We are just getting started. So, let me just get my pen here and we'll fill in some of these blanks. Just in case you don't know or didn't realize, these slides that I have follow the notes that I posted in D2L earlier today exactly. All I've done is taken screenshots of those notes to make slides out of them. So it's best if you have the printouts in front of you following along with everything I'm doing, but if not, keeping notes on your own paper is fine as well. But it really does help if you'll participate and work through these problems on your own while I'm working them as well. Okay, so a relation is simply a set of ordered pairs. And all ordered pairs are mappings of how to move in this XY plane to find a new position. So you're basically sending an input to an output if you start thinking about it in terms of functions, which we're going to get to here right now. So the set consisting of the first component, in other words, the X values of the ordered pair, is called the domain. So if you gather up all of the X values for that relation, that's called your domain. The domain is also known as the input or the independent variables. So the reason that they're called the independent variables is because those are the variables that you choose values for to plug in. Let's say we have an expression like 3x minus 7 equals y. So X is not one set number. Whatever you plug in for X is what's going to result in what you get out for Y. So if I plug in 2 for X there, then I'm going to get out -1 for Y, because 3 times 2 is 6, 6 minus 7 is -1. So that's where the word variable comes from. It varies, and you're always, well, I don't want to say always and use an absolute. 9 times out of 10, you're plugging into the X value, so that's considered your input or your independent variable, because your Y depends on what you've plugged in for your X, so that the Y is actually known as the dependent variable. So if I gather up all of the possible X's that I could plug in there, which in this particular case, since it's a linear function, that's all the real numbers. I can plug in anything I want for X. What if I plug in 0? Then Y ends up being -7. So all those X values that are possible are considered the domain. All of the possible output or Y values is known as the range. And I'll just remind you, these are the X, that's the X-axis, and this is the Y-axis there. The range is also known as the output or the dependent variable, because it depends on what you plug in for X. So I can actually write relations in many different forms. In this case, my relation is written in set notation. It's a set of points, and if I draw out the X values from that set of points and create a new set with them, That set is known as the domain. 1, 2, 3, 4, 5. If I draw out all of the y values, that set is known as the range. 2, 4, 6, 8, and 10. Maybe my relation is expressed in an XY table. 1, 2, 2, 4, 3, 6, 4, 8, 5, 10. There's no difference in these two things, whether set notation or table notation, if you will, an XY table. There's absolutely 100% no difference besides the way they look in those two things. And I'm going to go even further and say, well, what if I draw this on the graph? There's 1, 2, 2, 4, 3, 6, 4, 8, 5, 10. How many of y'all, your skin's crawling because I haven't drawn a line through that yet? Those points represent points on a linear function. But I'm leaving them as relations right now. I'm just drawing out the mapping of input to output. So I have a relation here, and it actually happens to be a function, but we'll talk about that in a moment when we get to that definition. There is no difference, once again, now between my graph and my table and my set of points. They're all the exact same thing. So give me a green check if you understand what a relation is. It's just a mapping of input to output. And you're ready to move on. Looks like everybody's ready. Good deal. Okay, so now we're going to talk about a specific type of relation. And this is what we will be talking about for the remainder of the semester. So this is very important. And that type of relation is called a function. Okay, so what makes a function special? A function is a relation in which each possible input value leads to exactly one output value. So each input sends to only one output. We say the output is a function of the input. In other words, y is a function of x. Let me write that down. We say y is a function of x when we're dealing with an xy equation there. The input makes up the domain, the output makes up the range. You already know that. Now, let's look at these diagrams here. This A diagram. So I've got P sending to M, I have Q sending to N, and I have R sending to N. Nowhere from my inputs, I did not send any one of my inputs to more than one output. For example, I did not send P also to N, sending P to two different places. If I sent P to two different places, it would no longer be considered a function. So for a relation to be a function, each input can only send to one and only one output. And here's a quick way to remember, especially if you're looking at an XY table. For it to be a function, you cannot have repeat input values. In other words, let's go back and look at this XY table. Let's say I had another one here, another value. Let's say I send 5 to 12 as well. It's no longer a function at that point because I've sent 5 to 2 different outputs. So green check if that's making sense so far. Okay, good deal. All right, so this one in the center, obviously it's a function. Each input sends to one and only one output. Now look at the last one. Not a function because I've sent Q to 2 different places. In other words, if I ask you, when I place Q into this function, what is the depending result that comes out? You couldn't give me one answer because it's either Y or it's Z. I don't know. It's both of them. It's not a function at that point. Okay. So how to determine whether a relationship is a function. So you want to identify the input values, identify the output values. If each input leads to one and only one output value, then it classifies as a function. If any one input leads to 2 or more outputs, it does not classify the relationship as a function. It is simply a relation at that point. So now I'm going to blow your mind. Y'all clear your heads for a minute because I'm going to give you a statement. It's going to blow your mind. Every function is a relation, but not every relation is a function. Every function is a relation, but not every relation is a function. Because you can have a relation that sends input to more than one place. But as soon as it does that, it cannot qualify as a function. Okay. So take a look at the relation down at the bottom. We have baseball players and we have their rankings. Is this relation a function? Is the rank of the player, is the rank a function of the player's name? Josh says yes. He gave a green check. Ashley, Lisa, green check or red X? What do y'all think? Lisa says yes too. Ashley says yes. Y'all are correct. Because I'm sending that player's name out to that rank. So my rank depends on whatever player I'm talking about. Is the player's name a function of the rank? In other words, is it possible that more than one player could be ranked second? I think it is. Oh, it's not? I don't know much about baseball. Okay, so I've got some yeses, but that's true. I think that multiple players can be ranked at the same rank, depending on their stats. And so the player's name would not be a function of the rank because I could send that rank to more than one player. Now, if we're just going with what's on the screen here, then yes. They're both, because we haven't sent anything from either side to more than one thing on the other. But if you think about it in general terms, it's probably no. But for our purposes here with this example, just what's listed, then yes, it's a function both ways. Okay. Determining if class grade rules are functions. In a particular math class, the overall percent grade corresponds to a grade point average. Is grade point average a function of the percent grade? Is the percent grade a function of the grade point average? Okay, so if your grade point average, if you score in the class a 0 to a 56, your grade point average is 0.0. 57 to 61 is 1.0, 62 to 66 is 1.5, 67 to 71 is 2.0, 72 to 77 is 2.5, 78 to 86 is 3.0, 87 to 91 is 3.5, and 92 to 100 is 4.0. Okay, so first question. Is the grade point average a function of the percent grade? In other words, when I take my percent grade, let's just choose a random percent grade, 63. If I have a percent grade of 63, will I ever be awarded any grade point average besides 1.5? So the first question we're asking, y'all are correct, Josh and Lisa. I will never be awarded anything besides a 1.5 if I have a 63% grade. So for the question, is grade point a function, FN, of percent grade? So answer that question. If I have a percent grade of 63 and it's always going to send me to a GPA of 1.5, is grade point average a function of percent? I've got one no, one yes. Josh, are you going to break the tie? A yes. Okay, Lisa's typing. Oops, did you mean this? Okay. I'm glad I didn't have to go back through that. Thank you, Lisa. All right, so yes. In this case, grade point average is a function of percent. Now, is percent a function of grade point average? Josh says no. Josh, do you want to use your microphone and explain why it's no?
I believe because there's multiple percent grades, so it would be it would have too many dependent variables.
Yes, you're absolutely correct. If I said, if I ask you the question, okay, I have a grade point average of 1.5. What was my percent grade? You wouldn't know what to say, would you? Because if I'm asking is percent a function of GPA, that means I would have to take GPA and send it over to percent grade, and it can only go to 1% grade. And you can see that each GPA goes to a range, multiple percent grades. So this is sending an input to more than one output. Okay, good, Ashley. I'm glad that made sense to you. So the answer to the first question, is grade point average a function of percent? Yes. Is percent a function of GPA? No. Okay. Yay. Using function notation. Okay, so once we determine that a relationship actually is a function, we need to be able to notate that it is a function in some way. We need to set it apart saying this is a special relation. It's a functional relationship. And when you get functions, you can put them into, you can program them into your calculator and stuff like that. You can graph them on your calculator. We'll look at some in a moment with the Desmos online graphing calculator. So there are various ways of representing functions. A standard function notation is one representation that facilitates working with functions. Okay, so let's say I have the equation. We'll go back to our 3x plus 7 is y. All right. So this is just written in variable notation, I guess. I don't know what you, I mean, it's a linear equation in two variables. Actually, no, it's not in standard form. It's in slope-intercept form. We'll get there later. But notice with function notation, we have this notation of this thing equaling y. Okay, so this f parentheses x in parentheses is what we call function notation. And what this says, how this reads, is y is, you know, you can replace an equal sign with the word is. So the is comes from the equal sign. Y is that side right there, all it says is function of x. In other words, I'm going to plug in some x value into an expression, and I'm going to get out a y value. So wherever you see y, you can replace that with, okay, when we say this quickly, we like to use jargon instead of saying a function of x. What we generally say is f of x. And what that means is a function of x. So I could rewrite this equation at the bottom, or this function at the bottom, saying 3x plus 7 is f of x. Same exact thing. So what this is asking is, okay, well, to fill in this side over here, you have to figure out how x functions in the equation or in the expression on the other side. And what this allows me to do, so let's say I have f of x is equal to 3x plus 7. This allows me to now ask you, well, what do you get if f is 2? What's f of 2? What is the function of 2 in the expression on the other side? And that would tell me to plug 2 in wherever I see x to figure out that f of 2 is 6 plus 7, which is 13. So the function of 2 is 13. I could just as easily write this in point notation and say when I graph that line, 3x plus 7, the point 2, 13 is going to land on that graph. I can tell y'all are skeptical and you don't believe me, so I'm going to show you. You skeptics. I'm just kidding. That was my poor attempt at humor there. I try to make myself laugh, and it usually doesn't make anybody else laugh. I'm pretty silly. Okay, so 3x. Thank you, Josh. Thank you for the sympathy ha-ha there. Okay, so 3x plus 7, we have a line. And notice we said, okay, well, when we plug 2 in for our x value, we get out 13. And when I click on, let's see if I can hit it on the nose. 2, yeah, There we go. 213 is a point on that line. So, just like I showed you on the first page of this lesson, there is no difference in the function notation of that point. There's no difference in the equation that you write out or the expression there. There's no difference in writing it as a point. There's no difference in writing it in an XY table. And it shows up on the graph of that function. Was this a good enough connection for you with all that material? And I'm being serious when I ask that question. Does it make sense now why we have this notation and how all these different ways of writing functions, whether it's a set of points, an XY table, or on a graph, they all mean the same damn thing? Josh, are you good? Okay. That's why I teach them together, because there's no need to separate them in your mind because they're nothing different from the other thing. It's just a new way of looking at it. Okay, so what the rest of this garbage on the page says, and all this stuff comes straight from your book. All I do is either copy and paste or take a screenshot and paste it into the notes. So you can go back with this lecture with your book open and you'll be able to follow it step by step through your book. Okay, so we can use any letters to show a functional relationship. So say, for example, every point in the plane that we want to talk about comes in the form of AH. Maybe that's age depends, or height depends on your age. I think that's actually what that came from. So if you think about a child growing, the older they are, the taller they're usually getting until they reach the plateau point, and then you actually start shrinking. So H of A says every point in this plane is of the form A, that's where I plug in, that's my input value, and I get out some H value. So if I am plugging in 13 years old into whatever this model is, maybe I get out, I don't know, 65 inches, whatever. It's a pretty tall 13-year-old, but I've seen taller. All right, so, oh yeah, it is age and height. All right, so we can also give algebraic expressions to plug in. So let's take this same example at the bottom. F of x is equal to 3x plus 7, but now let's see what f of a plus b would look like in 3x plus 7. So wherever I see x, I'm going to plug in a plus b. 3 times a plus b plus 7. I have to distribute that 3. That's 3a plus 3b plus 7. So it looks pretty funky, but every point in this plane is of the form a plus b, comma, that's my input, 3a plus 3b plus 7 is my output. And then if you start choosing A's and B's, you can start getting actual values for that. All right, so a function n equals f of y. In other words, I'm going to be plugging in y and getting n out for that. And this gives the number of police officers in a town in year Y. So what does the expression f of 2005 equals 300 represent? One of you please use your microphone so that everyone watching the video can hear as well. What does f of 2005 equal 300 represent in regards to this equation? And if you don't know, it's okay.
Oh,
I want to at least give you a chance.
300 represents N and 2005 represents year, Y.
Yes, very good. So what this says is for whatever town this is, in the year 2005, there were 300 police officers. Excellent, Ashley. Thank you for being brave and stepping up there. All right, so let me just write that for the sake of the video. So in 2005, this town had 300 popos, police officers. All right. Use function notation to express the weight of a pig in pounds as a function of its age in days D. So we'll call the weight W and age in days D. So what this says is the weight of the pig has got to be equal to that function of how old it is in days. That's how you'd write the general expression there. Green check if you're cool with all this. Okay, great. I got a bunch of smarty pants in the room tonight. That's awesome. I love having smart students. Makes my job easier. Thank you for the applause, Lisa. Thank you for the laughter, Josh. All right. Given a table of input and output values, determine whether the table represents a function. So you're just going to be looking at the inputs and outputs and seeing if it's sending any input to more than one output. So that first table, we have inputs of 1, 2, 3, corresponding outputs of 10, 100, 1,000. Green check if it's a function, red X if it's just a relation. Okay, so I've got 1 answer, 2 answers, and 3 answers, and you're all correct. This is a function. All right, second table, -3, 0, 4. Outputs are 5, 1, 5. Ooh. 5, 1, 5 on the output. Lisa says it's a function. Ashley says it's not a function. Josh is the tiebreaker again. Oh, it actually changed. Okay, yes, y'all are all right. This is a function. It's okay to double up on your output because you're not sending your input to more than one place. That's the only stipulation for a relation to be a function. Now, of course, I had to throw one in that wasn't. So this last one obviously is not going to be. I have inputs of 1, 5, and 5. And I have outputs of 0, 2, and 4. So I'm sending 5 to 2, and I'm sending 5 to 4. Let me show you what that would look like on a graph, because here's an important key point. There's my little hand-drawn awful graph. So I have 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay. So I have the point 1, 0. Right here. I have the point 5, 2, and I have the point 5, 4. So whenever you have a relation that is not a function, so this is not, that is not a function, what's going to happen because you've sent an input to more than one output, you're going to have points that start stacking on top of each other. Because I've sent 5 to 2 different outputs. This is what leads us into our discussion of the vertical line test. So just keep that in mind until we get there. When you send an input to more than one output, it vertically stacks your points on top of each other. Okay, when we know an output value and want to determine the corresponding output, when we know an input value, and want to determine the corresponding output value for the function, we blank the function. Whenever we plug an X value in to get our output value out, that's called evaluating. Or actually, I shouldn't put it in the gerund, I think, gerund form. Any of you English majors are out there? Evaluate. Yeah, that's right. Evaluate the function. So it's called evaluating when you plug a value in and get a corresponding value out. Evaluating will always produce one result because each input value of a function corresponds to exactly one output value. So they're driving that point home, obviously. When we know an output value and want to determine an input value that would produce that output value, we set the output equal to the function's formula and solve. So now we're dealing with an equation. You evaluate an expression, you solve an equation. Solving can produce more than one solution because different input values can produce the same output value, just like we saw in the tables on the last page. Okay. So given the formula for a function evaluate, so you're going to replace the input variable in the formula with the value provided and then calculate the result. So I'd like for all of you to grab some paper and a writing utensil. And here's our function. F of x is equal to x squared plus 3x minus 4. And the first thing we want to figure out is what is f of 2. Take a moment and see if you can figure it out. I'm going to go ahead and start writing it on the board, but see if you can beat me to it and type your answer into the chat window. So we have 2 squared plus 3 times 2 minus 4. 4 plus 6. Okay, I've got two different answers in the chat window. Interesting. 4 and 6 is 10 minus 4. Josh is already admitting defeat in the chat window over there. For those of you watching the MP4 version of the video, you don't see the chat window. You have to watch the Blackboard Collaborate version of the video to see the chat window, but Josh admitted defeat just for those of you watching the MP4 version of it. All right, so this is A. And here's B. They say, okay, well, what about f of A? Oh, well, that's easy. You just stick A wherever you see x. So A squared plus 3 times A minus 4. A squared plus 3A minus 4. That's your output. It doesn't feel good, but you did it. It's no big deal there. All right, so the next two are going to take some room. So I'm actually going to grab what we got for f of A, because we've got to use it for the last one. I didn't grab the whole thing. There we go. And we're going to go to our next page. All right. So let me paste this. There's f of A. Now try f of A plus h and see what you get. It takes a little more work than f of A. I'm going to change colors here. Now we're going to try f of a plus h. And go ahead and try it on your own because this one's a little tricky. So that looks like a plus h squared plus 3 times a plus h minus 4. Okay. Just so you don't put the cart before the horse with working on your own there, this a plus h squared is absolutely 100% not a squared plus h squared. It is a plus h times a plus h. There's an entire middle term there that you have to get. It's an AH term. This 3 is going to distribute. So plus 3a plus 3h minus 4. Now I have to come back and do all this business. Fun. A squared plus AH plus AH plus H squared plus 3A plus 3H minus 4. Okay. So, now combining all my like terms together, I've got like terms here, and that's it. Those are the only like terms I have. So I get a squared plus 2AH plus h squared plus 3a plus 3h minus 4. Okay, so this is an extremely important concept. Well, it will be to you when you get into calculus. This right here is known as the difference quotient. That says quotient. I know it doesn't look like it, but it does. And it will be the very first thing that you study in depth in a calculus course. So that's why they've gone ahead and slipped it in on you. What this says is take the polynomial that you got for f of a plus h. You're going to subtract the polynomial that you got for f of a, and then you're going to divide h out of everything. So we're going to do the difference. This is D, this is C, this is B. We're going to do the difference quotient. And it's going to take all that room probably. Okay, so f of a plus h, and I'm going to plug in parentheses. That is a squared plus 2ah plus h squared plus 3a plus 3h minus 4. Here's why it's called the difference quotient, because you're subtracting. I'm subtracting, and I'll do this one in aqua color. Subtracting that polynomial, a squared plus 3a minus 4. And after I hash all that out, I'm going to divide everything by h. All right. Hopefully y'all are not falling asleep on me yet. So I'm just going to point out there's an understood 1 here that gets distributed to all those terms. There's an understood negative 1 that gets distributed to those last 3. So that's what I'm going to do, and I'm going to keep it color-coded for right now. A squared plus 2ah plus h squared plus 3a plus 3h minus 4. And now I have negative a squared, negative 3a plus 4. And that's all divided by h. Okay, here's the only satisfying part about calculating the difference quotient, because you get to slash things out. Positive a squared, negative a squared. Positive 3a, negative 3a, negative 4, positive 4. Your f of a will always go away. It's always going to have its opposite in the f of a plus h that will zero it out. So now here's what I'm left with. 2ah plus h squared plus 3h divided by h. Notice, look at all the terms in your numerator. They all have a common factor of h. And when I divide that out, I'm left with 2a plus h plus 3. And that's being divided by h. Now that my h in the numerator is a factor, I can divide it. So you did all that business to come up with 2a plus h plus 3. Don't worry about what that means right now. You will soon find out, I promise. But for right now, you just need to make sure that you can go through the motions of finding the difference quotient, because it's challenging and it takes practice. It really does. This is one of those types of problems that students just get bogged down in. Just take it bit by bit. Find your f of a plus h, find your f of a, and I like color coding. Even if I'm just working on my own, I color code things so that I can see what I've got, what I'm dealing with. So if you want to use colors all over your paper, knock yourself out. It helps me. Okay, are there any questions floating around about anything we've done on this page? Okay, Lisa, do you want to go back a page? Where do you need to go back to? And Ashley, I see you're typing too. Foiled by the difference quotient again. Oh, not back. Just want to make sure. What if there's something in front of the? Oh, that's an emoji. It's okay. It's an emoticon. What if there's something in front of the f of x? Is that what you were asking? Okay. What if there's something in front of the f of x, like a number or a negative? Is there a question in your homework, Lisa, that you're thinking about?
Hey.
Okay, I see you got your mic on.
So in our homework, there's one that, okay, it's f of x equals x squared divided by x minus 1, and then solve for 8 f of x.
Okay, let me open up a new page, and I want you to rattle that problem off again.
Okay, so it's f of x equals x squared divided by x minus 1.
Okay, and they're asking what is 8? That?
Yes, that's correct.
Okay. So what that's telling you to do is multiply 8 by that entire function. So 8 times this entire function. And I'll just point out, this is a really good one to look at. Thank you for bringing this, Lisa. This is really an 8/1. When I work with fractions, I like everything to look fractiony. and we multiply fractions straight across. So the numerator ends up being 8x squared. Now, if that denominator of the 8 had been anything but a 1, you'd really want to pay attention because that's distribution. But since it's a 1, it doesn't change anything. So we end up with x minus 1. So 8f of x is equal to 8x squared over x minus 1. Did that help, Lisa? Okay, Lisa says it helped. Okay, and Ashley got her question typed in. Okay, so I'm going to go back because it's about question C. Okay, so just for the sake of the video, Ashley's asking about this one right here. Okay, so for question C, for A times H times A times H, I see you got AH plus AH. Okay, that's a great question. She said, would it not be AH plus HA? I hope this makes sense. My last math class was 5 years ago. You're not alone, by the way, with having a math class way long ago, and now here you are in college algebra. Okay, so your question is excellent, Ashley, and Lisa's agreeing with you with having been years out of her last math class as well. Okay, so I'm going to answer a question with a question. And I assure you my students love it when I do this. Okay, so when the variables are touching each other, we know that's multiplication. So my question for you, Ashley, is 3 times 2 the same thing as 2 times 3? Yes, and I'm glad you got that right. I'd be worried if you didn't get that correct. So, multiplication is commutative. In other words, you can flip-flop it around. You can commute the numbers, and you're going to end up with the same thing. So, AH equals HA. Does that answer your question, Ashley? Does that help? Okay, good deal. She's giving me a thumbs up for those of you that can't see the chat. All right. Anything else before we move off of difference quotient? Like I said, I know difference quotient is a doozy. And that is a highly technical math word there, mathematical word, doozy. Once again, I'm only entertaining myself here. Okay. Evaluating functions expressed in function form. So some functions are defined by mathematical rules or procedures expressed in equation form. If it's possible to express the function output with a formula involving the input quantity, then we can define a function in algebraic form. So given a function in equation form, write its algebraic form. How do we do that? We solve the equation to isolate the output variable. In other words, y equals 3x plus 7. And then you're just going to replace the output value with f of whatever, f of x, if it's y equals 3x plus 7. So to go from algebraic form, y equals 3x plus 7. This is algebraic. G-E-B-R-A-I-C. We can move to function form by just replacing the output with f of x. Okay. So, finding an equation of a function. Express the relationship 2n equals 6p, plus 6p equals 12 as a function p equals f of n if possible. So, which variable am I supposed to be isolating? Yes, the p. So, let's do that. 2n plus 6p equals 12. To isolate the p, the first thing I'm going to do is subtract 2n from both sides. And I have 6p equal to 12 minus 2n. Divide every term by 6. And I end up with p equals 2 minus 1/3 n. Okay, so since I was able to write p equals blah, 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 n, I have put p in terms of n. Let me write that down because that's important language right there. At this point, I have put p in terms of n. In other words, now p is a function of n, because I'm going to plug in some n value to figure out what p is. Since I have put p in terms of n, I can rewrite this equation in its function form. Well, that means the function of n is 2 minus 1/3 n. Y'all cool? Ashley, was that okay? Okay, great. Okay. Does the equation x squared plus y squared equal 1 represent a function with x as the input and with y as the output? If so, express it as a functional relationship. So I start with x squared plus y squared equals 1. And I'm trying to isolate y. So I'm going to subtract x squared off of both sides. Y squared is equal to 1 minus x squared. And then I'd have to take the square root of both sides to get that square off the y. And that's going to give me, oops, I grabbed a white pen and y'all can't see when I write with a white pen. Y equals, you have to take into consideration the positive and the negative of the root. And here's why. Let's say I have x squared equals 9. This is asking, what can I square to make 9? So I take the square root of both sides, and I have to consider I could have squared positive or negative 3 to make 9. So you have to consider the positive and the negative whenever you are solving an equation using the root property, the square root property. You have to consider that there could have been a positive way of arriving at that or a negative way of arriving at that. So what this says, think about this. What happens if I plug in 0 for x? If any of you want to tap on your microphone talk button and tell me what happens, what kind of output do I get when I plug 0 in for x? Anybody?
Is it not a function?
It is not a function, Josh. Why are you saying that?
Because you can't have 0 as your output?
Not quite. But you're sort of there. If I plug in 0 for x, 0 is fair game to plug in for x. There's nothing wrong with plugging an input value of 0 in to this function. So that's going to make it y equals positive or negative square root of 1 minus 0. So I've plugged in 0. So this means y is equal to the positive or negative square root of 1, which means y is equal to positive or negative 1. So what have I done with an input of 0? When I plugged 0 in, what did I get out? This isn't a trick question, it's sitting right there. Lisa's typing.
One.
Well, yeah, go ahead, Josh. The other number is what came out and the square root. Yeah. So what has happened here? I have input one value of 0, and what I got out were 2 different values. So this has sent an input, one input to 2 different outputs. Yes. So that's why this thing is not a function. You cannot write it in function form. This is how you write this equation. By the way, just for the curious, that's the equation of a circle that is centered at the origin with a radius of 1. So there's no way I could rearrange that equation so that I solve for a single y and get one value out. That means you can't put these into your graphing calculator because you have to be able to get something into function form to put it in your graphing calculator. You can put it in piece by piece. You can have one function equaling positive 1 and one function equaling negative 1. Let's take a look. So I have the positive square root of 1 minus x squared and the negative square root of 1 minus x squared. Let's go take a look. So I have the positive, let's see, square root of, oh shoot, I've already forgotten it. What was it, 1 minus x squared? Cool, thanks, Lisa. I've got a terrible memory. And I got to quit saying that because I reinforce it every time I say that. You create your own reality. So I just need to create a better memory for myself. So there's half the circle. And then we had negative square root of 1 minus x squared. There's the rest of the circle. Is a circle a function? No, you're right, Josh. It's not. Circle is not a function. You're correct, Lisa. Not a function. You've got inputs throughout the entire circle going to 2 different outputs. I put in 0, and I get out 1, and I get out negative 1. I get 1, and I get negative 1. So that's the equation of a circle you were just looking at, and it is not a function. I hope that was helpful for you to see it like that and not just a waste of precious lecture time there. Okay, let's take a look at this next one. Let's see if we can get y by itself and not have anything funky going on with x to give us more than one output value. So x minus 8y cubed equals 0. So I want to try to solve for y. I'm going to subtract x. Negative 8y cubed equals negative x. And I'm going to divide both sides by negative 8. And now I have y cubed equals positive 1/8 x. Or I could write that x over 8. I'll write it x over 8. Let me change that. For some reason, that just doesn't feel good tonight. There we go. So x over 8. Now to undo something that's cubed, I take the cube root of both sides. We don't have the same issue that we have to worry about with square roots as we do with cube roots. So I get y equals the cube root of x over 8. So think about it. If I plug a value in for x, let's use 0 because that's nice and neat, am I going to get more than one value out? Josh says no, and you're correct, Josh. You're good this time, Josh, yay. If I plug in 0, I get y equals the cube root of 0 divided by 8. That's y equals the cube root of 0. What can I multiply by itself 3 times to make 0? Well, that's 0. So since I only get one output, I can rewrite this is a function. I can rewrite that as f of x is equal to the cube root of x over 8. All right. We're getting there, I promise. And like I said, I knew this lecture was going to go past an hour. I'm so sorry. If you need to go, please go. All right, so evaluating a function using a table. So if we look at what it's asking us to do, it says evaluate, we have this function g of n. And it says, okay, well, if I plug 3 in for n, what do I get out of the function? Type your answer into the chat window. I've told you, looking at the graph is no different from looking at the equation, is no different from looking at a table of values, is no different from looking at a set of points. So when I plugged 3 in to the function for n, what did I get out for g of n? How did the n of 3 function? Yes, Josh, that's it. So when I plugged in 3 into the function, I got out 7. So g of 3 is equal to 7. Lisa, Ashley, are you all okay with that? Okay. What this next question says, well, what did I have to plug in for n to get out 6? So this is the difference in evaluating and solving. You've got to kind of flip your thinking. And Lisa, you're absolutely correct. So I had to, n here had to equal 2 in that case. That's solving the equation. Remember a while ago we talked about the difference in evaluating it and solving it. So it's the matter of flipping and asking. Evaluating, you're asking, okay, if I plug this in for the input value, what do I get out? When you have to solve the equation, you say, here's the equation, and how did that equal 6? What did I have to plug in? What did n have to equal to get 6 out? So are y'all good with evaluating and solving from a table? Okay. I'm trying to boogie. I'm trying to move. Okay, same thing, except now we're doing it with a graph. This particular one says, Well, if I plug in -1 for my input value, what do I get out? So when I plug in -1 to my function, I get out 4. F of -1 is 4. Now, these can be tricky with the graphs. Did y'all see that? It's a visual thing. Josh, did you catch on to that, or do I need to go over it again? Okay. All right, the exact opposite question. What do I have to plug in for X to get an output of 1? Let me switch colors here. Yeah, so we've got 2 answers here because this is not what we call a one-to-one function. It is a function, but it's not a one-to-one function, and we're about to talk about what a one-to-one function is. So if I want an output value, that's my Y's. If I want an output value of 1, I could have plugged in 0, or I could have plugged in 2. So X had to equal either 0 or 2 in this case. That is the solution to the equation. Okay. So here we are. What the heck is a one-to-one function? Some functions have given output values that Some functions have a given output value that corresponds to 2 or more input values like we just saw. However, some functions only have only 1 input value for each output value, as well as having only 1 output value for every input. We call these functions 1 to 1. So real quick, I'll give you a visual example of one that is and one that isn't. The quadratic. This is not, I'll just use numbers. I'll have to write all that out. This is not 1 to 1. However, the cubic is 1 to 1. So for a function to be 1 to 1, you should be able to put a horizontal line anywhere on that function, and it's only going to pass through 1 point if it's 1 to 1. Notice if I put a horizontal line going across the parabola, I hit 2 points. It's not 1 to 1. So if each percent grade earned in a course translates to 1 letter grade, is the letter grade a function of the percent grade? Yes. Josh, you're correct. In other words, if I tell you you have an average in my class of 87%, there should be no question about the fact that you're going to get a B. It shouldn't be questionable if you're going to get a C or not. You're going to get a B. Is that function 1 to 1? Lisa says no. Lisa, do you want to explain why no?
Because I'm sorry, okay, so it was the other way. So 80, the numbers anywhere between 80 and 89 would be, will you rephrase it, ask the question again?
You're correct. You're absolutely correct. You're just getting confused with your own words. So I'll put it into language for you. So, no, this function is not one-to-one. It is a function because if you choose a percentage, you'll always know that one grade you're going to. However, it's not one-to-one because you could have an 80 or you could have an 87 or you could have an 83 or you could have an 89 and it's all going to be a B. So it is not one-to-one. Yeah, I knew that's what you meant, Lisa. Okay, using the vertical line test. So the vertical line test, the vertical line test, this is a test for if something's a function or not. And all it says is you should be able to put a vertical line anywhere on the graph and only pass through one point because we know when something's not a function, it's going to start stacking points on top of each other. So that first one's a function. Second one, not a function. Third one, not a function. The horizontal line test is a test for one-to-one. So if I put a horizontal line anywhere, this is not one-to-one. It is a function, but it's not one-to-one. This is not a function, but it is one-to-one. This is not one-to-one, and it's not a function. Are y'all cool with the horizontal and the vertical line test there? So vertical line test is test for a function. Horizontal line test is test for one-to-one. Awesome. Does this graph represent a function? Yes, everybody got it. And I can't write a Y. Yes. Is it a one-to-one function? Josh, you say yes? Ashley, Lisa, what say you ladies? Ashley says no. Lisa says no. Josh, you want to rethink? Girl power here. Okay, Josh changed to no. So, the function test, Ashley's applauding for girl power. Function test is the vertical line test, so it passes as a function. However, if I come back with the horizontal line test, it fails. So, not one-to-one. And then this is just below, is just a description of the horizontal line test. It's on your page, on your lecture notes. Okay, we're going to blaze through these because we're already 20 minutes past and we could spend an entire lesson on just these. I just want to go through and show you what we call parent functions or basic toolkit functions. It will be to your benefit to learn the shape, what the function itself looks like, and a few of the values in the XY table that create the shape. So we have the first one, which is constant. F of x equals c, where c is some value. In this example here, this would be f of x equals 2. That says no matter what I plug in for x, I always get out 2. And that always comes out to a horizontal line. F of x equals some value is always a horizontal line going through that value on the y-axis. Then we have the identity line, f of x equals x. So this is a line that goes through the origin. So whatever you plug in for x, you get out for x. That's why it's called the identity, because whatever you plug in, that's what you get out. Anything is always itself. It's its identity. So it goes through the origin, and it has a slope of 1 if you want to start thinking about slope-intercept. The absolute value makes a hard V shape. Because think about it. It's not 1-to-1, because if you have the absolute value of -1, that's going to be 1. But if you have the absolute value of 1, that's also going to be an output of 1. So this is not 1-to-1. It fails the horizontal line test. But it makes a hard V at a vertex. And I keep pointing that out because your quadratic, which graphs as a parabola, is a soft U. It's a curve. It doesn't meet at a vertex. And this is what something that's squared looks like. And obviously I did a bad job cutting and pasting because I got the next labels for the next slide there. So also not 1-to-1, because I'm going to get the same thing when I square -2 as when I square +2. They're both 4, so it's not 1-to-1. Last slide, I promise. So I have my cubic here, and this is a function, and it is 1-to-1 because when you cube a negative number, you get a negative number out. Because you're multiplying a negative by itself 3 times, so you still get that negative that comes out. Then we have what we call the reciprocal function, and that's 1 over your variable, x. So it does produce a function, and that function is 1-to-1. Reciprocal square, 1 over x squared, it does produce a function. However, this thing is not 1-to-1. It kind of makes a volcano shape. Square root, take the square root of a number. Notice this one stops. It doesn't have an arrow on the end, and that's because you don't want to input the negative numbers here because you're going to get imaginary numbers out. If you try to take the square root of -4, what can I multiply by itself to make -4? Everybody always sits there dumbfounded because it's an imaginary number. There is no real number that you can multiply it by itself to get -4. So that's why this particular function has what we call a restricted domain. In other words, you can't plug in anything you want and get out a value on the function. Cube root you can, though. The cube root's not restricted because you can take the cube root of a negative value. The cube root of -8 is -2 because -2 times -2 times -2 is -8. So we do have a function, and it is 1-to-1 there. That's all I have for y'all. Oh my gosh, thank y'all for hanging in 25 minutes past the hour. I knew this was going to be lengthy. Thank y'all so much for staying and participating in the lecture. I truly appreciate it. I hope this was helpful for you. You're welcome. And y'all can log out whenever you're ready. Have a great weekend, unless I see you at tomorrow's lectures.